Problem 60, just like the problem we just did, we have something similar to 2x plus 6 is greater than 20. And what we would do in this case over here is we would subtract 6 from both sides. And that's exactly what we're going to do over here. We're going to subtract 6 from both sides. And when we do that, remember, when we have absolute value bars, we cannot manipulate what's inside. You can only change what's inside or move around what's inside once the bars are gone. So anyway, the 6 minus 6, that's 0, and we're still left with 2 times the quantity absolute value of 4t minus 1, and that's greater than 14. Over here, the 6 minus 6 would cancel, and we'd get 2x is greater than 14. So we have the similar equation, similar inequalities here, and over in this case, on the right-hand side, you would think, okay, well, let's go ahead and divide by 2, and that's exactly what you should do to get the x by itself. So if you would divide both sides by 2 to get the x by itself, then you must divide both sides by 2 to get the absolute value bars, or the absolute value expression by itself. So 4t minus 1 is still inside the bars. That's good. So we don't want to move that around. And here you might be inclined to add 1 to both sides. You can't do that. Remember, you've got to go ahead and remember that in this case, we have to change this. We have to rewrite this expression using 2 separate inequality symbols. Just like when we had equations, we rewrote the expression using 2 separate equations. So since this is a greater than, so we have greater, this is an or statement. It says that 4t minus 1 has to be more than 7 units away from 0. So if you think about what a number line would look like and what that would look like graphically, if we're more than 7 units away from 0, here's 0, there's 7, and there's negative 7, because both 7 and negative 7 are 7 units away. But what we want is we want 4t minus 1 to go that way, to be greater than 7, or we want 4t minus 1 to be that way on the other side of negative 7. So what this says here is that 4t minus 1 has to be less than negative 7, or 4t minus 1 has to be greater than positive 7. So we get 2 separate inequality statements. And so when we do that, now the bars are no longer there. Now we can go ahead and solve for t. So in solving for t, we're going to add 1 to both sides. I should have done that in red. The negative 1 and the positive 1 cancel each other out. We get 4t is less than negative 6, or when we add 1 to both sides here, we get 4t is greater than 8. So then, do that in red now. So now we have our, we can solve for t by dividing both sides by 4, and we get t is less than negative 6/4, which is negative 3/2. Or we have to divide both sides by 4 to get the t by itself. The 4's cancel, and we get t is greater than 2. So the real numbers that make the original inequality true are the real numbers that are less than negative 3/2, or the real numbers that are greater than 2. So there are plenty of numbers, in fact an infinite number of them, that are less than negative 3/2. So there's negative 1, negative 2, negative 3/2 is right there, negative 1.5. And then we have 2, 1, 2. We'll put a 2 there, and then let's go ahead and draw the graph. Let me go get my marker. So I got my marker, and remember, less than negative 3/2 means an open circle on negative 3/2, and we will shade everything to the left. And then greater than 2, all real numbers greater than 2, we can shade everything to the right of 2. Now here's a kind of a cool way you could test out whether or not you got this right. So what we want to know is if we shaded the correct real numbers. So all the real numbers that are shaded, this is the key to understand this. If you shaded a real number, it means that that real number should make the original inequality true, right? So if you shaded it, it means that it's a solution. If you didn't shade it, it means it's not a solution. So here's a quick way. Look at that 0 right there. 0 seems to always be the easiest number to plug in for any variable. And so let's take the original inequality and we're going to replace t with 0. Now, if you get this, this is really kind of neat because then you really understand. So by replacing t with 0, we should get, since we didn't shade 0, we should get a statement that's false. Understand? We should get a statement that's false. So let's go ahead and multiply this out. 4 times 0 is 0. 0 times -1, or 0 minus 1 is -1. The absolute value of -1 is 1. So what we really have here is this whole thing here is just 1. 2 times 1 is 2. 2 plus 6 is not greater than 20. So 8 is not greater than 20. So that means that 0 did make the statement false. That is a good thing because we didn't shade 0. Well, let's pick a number that we did shade. Let's pick 10. So we shaded 10, certainly. And if we shaded 10, that means that 10 should make the statement true. So if we replace t with 10, and we're going to do that right now, let's see if we add 6 to that, if we get something that's greater than 20. That's the question. And that was the question there. So 4 times 10 is 40. 40 minus 1 is 39. 2 times 39 is 78. And then 78 plus 6 certainly is greater than 20. Check. So we shaded 10 because 10 makes the statement true. Now, again, we can't, there's an infinite number of numbers that you shaded, but nevertheless, we tried a number that's on the unshaded part. We tried a number that's in the shaded part to the right, and if you really wanted to, you could try a number that's shaded to the left. Let's go ahead and try -1,000, and we could just kind of, if we shade -1,000, we can kind of eyeball that. 4 times -1,000 is -4,000 minus 1. The absolute value of that would be a huge number, bigger than 4,000. Multiply that by 2 and you get 8,000 plus 6 is greater than 20. Check. So if we try any number in this shaded region, any number in the other shaded region, we'll see that all of those numbers make the original inequality true. Any number that wasn't shaded should make the inequality false. So we're pretty confident we got the right answer.